now going to hand it over to Anna to take us through AI, ML, and deep learning.
Thanks, Kevin. Hi, everyone. I'm going to actually flip from the slides for a second, just for a brief second, so you can see I exist if my camera works. Or it won't work. So you're just gonna have to take my word for it that I exist. My name is Anna Hoffman. As Kevin said, I'm a data and applied scientist on the SQL team at Microsoft. Before the SQL team, I was working on the AI engineering team at Microsoft. So I initially, just very short story, I initially came over from AI engineering to help bring more ML into the data space, specifically the SQL space. So this is a session I put together. I see a few of you have started using this Slido link. So I'm actually going to share that screen. Let's see. Hopefully you guys can see that. This is just an idea I had. This is the first time I'm doing this. Sometimes these remote sessions where you can't see the person and the person can't see you paying attention or not paying attention, it's hard to be engaged. So I just added a few of these to see, see at least where you guys are at. And then after we have the questions, you can also answer you can also use this to ask questions. So if I switch over to Q&A, you could see there would be Q&A here as well. You can join on your mobile phone via the internet app or on your computer. And if you don't join, that's cool too. Looks like we've got 3 responses. So thank you for the 3 of you that are here today. 4. But there's a few questions, so maybe I'll leave it here for like 5 more seconds and we'll try the next poll. And if we still don't have that many people, then we will just do something else. So it looks like I was wrong in my assumption of who was going to be in this talk. For any of the folks who are other, I don't know if you have the capability to say what you do, I would be certainly interested. Okay, well, this is great. I like the responses that we're getting. For some reason, like I said, this is my first time doing this. I haven't figured out how to do multiple questions at once. Oh, we have a data scientist, very cool. So we're gonna go ahead and skip to the next question, which is how comfortable are you with the differences between AI, ML, and deep learning? So if you wanna take a second, you should be able to see this poll now as well. Okay, we got some 3s, 2s. So just take a few seconds. This just gives me an idea of where to go deeper, where to spend more time, and where we can skip. Great, so I gotta be honest, I was kind of anticipating a lot of people being in that one category, but that's totally fine. We can spend some time not going as deep on certain things. And then if we take a look at the third one, this is just for me. I know this is a data science and SQL Server user group, so I'm assuming that, yeah, we're gonna get a lot of people that are comfortable with Azure and SQL, which is good. And maybe I'll show you something that you've seen before or something you haven't seen before, and then some of the options that you get in Azure or in things like SQL Server 2019. Cool. So like I said, I'll be monitoring the questions over here throughout the session, and I think Kevin will too. So if there are any questions, feel free to either, I don't know if you have the ability to come off mute, but either come off mute or just tell Kevin and we'll try to answer your question.
Yeah, I'll relay anything that comes in here.
Okay, awesome. Thanks, Kevin. Okay, so with that, I'm going to switch back to the slides. And again, that link is there if you need it to get to the questions. And I'll try to put that link every now and then in the slides so you can see them. Okay, so let's go ahead and get started. What are we going to talk about today? We're going to talk about data science, AI, ML, deep learning, and really the relationship between all of these things. I will dive into a few examples of AI and ML. But to be honest, when I originally created this, and my purpose I think today as well, is to give you a glimpse at deep learning, because I think this is becoming a new thing that is becoming more and more common. So we'll look at an example of that, and we'll actually get into the math behind it. I don't want anyone to be overwhelmed by that math. So just know when we get there that there are lots of packages that allow you to avoid the math. I just think in understanding things, and it seems like a lot of people are from a SQL Server background, like a lot of times you learn by figuring out how those things work, and then you can apply principles on top of it and not have to do everything from scratch. So that's what we're going to do today. So we're going to start by talking about data science. And this is kind of an umbrella term, but just to explain it briefly, it comes from two ideas. This idea of data analysis, which all the data people in the room or watching this are very familiar with the topics in this list, I would assume. And it's also the combination of data analysis with the scientific process or the scientific method. You might remember learning about this in school, you might not. Either way, that's fine, but basically the idea is that you have a question, you make a guess or some sort of hypothesis, and then you create a test that either accepts that hypothesis or rejects it, so you can have some sort of result. And then ideally there's an action that you take because of this. You don't just go through this process and say, interesting. More often than not, you're trying to make some sort of action. And then these topics of AI, ML, deep learning come into play, ML and deep learning being a subset of that greater theme of artificial intelligence. In the bottom left-hand corner, you'll see a link for the TDSP. So the TDSP is the team data science process, and those of you doing machine learning are probably familiar with this or some form of this. This is just, the Microsoft-sponsored process that we recommend, but I think it's pretty good. Basically, it takes you through a data science lifecycle. So similar to that scientific method, but kind of tying it into the data analysis as well. So you see, first you have your business understanding, and this is when you develop that question. Then you go into your data acquisition, your data understanding, your data engineering. This is really, in my opinion, where the complicated stuff happens. A lot of the modeling is just leveraging an algorithm that exists and then just tuning it as needed. And you have different data sets here. We won't get too much into that here today, but typically you have a training and a testing data set, and the training data you use to train your model, and then the testing data set hasn't been seen by the model before, so you're able to kind of evaluate which model is best based on which one performs the best on that unseen training data or testing data. And then you deploy it, and of course this is all an iterative cycle, so at any given point you might cycle back to a different step. But this is kind of the team data science process in a nutshell. The link that I shared, and you guys will all have this deck by the end of this, that link goes into detail. They have sample Jupyter notebooks, they have sample project files, they've really got everything to take you through any sort of data science lifecycle. So that's like the biggest umbrella that there is. Now, if we take a quick look at history, so in the 1950s, that's when this artificial intelligence thing started getting really big, and it was really for two reasons. One, computers were starting to be more and more of a thing, more used and useful and understood. So one, we thought, we're great at computers, we get computers. So we're going to be able to figure this out, because two, humans are super predictable. So anything a human might want to do, we can predict it. So Basically, they said, like, a kid with a burger or a salad, like, we know they're going to pick a burger. So that was kind of the beginning of artificial intelligence, and it's really just this idea of mimicking human behavior in some way, shape, or form. Now, it turns out they weren't actually able to program humans perfectly as easily as they thought. There was actually a period in here called the AI winter. It's kind of interesting to read about. But then in the 80s and 90s, this idea of machine learning came about, and really it came in the era of data mining and using statistics and kind of combining symbolic logic and data mining. And with computers evolving, we also began to be able to have more compute and be able to process more data. So I think we were able to really mature in this machine learning space in many areas. Now, what changed in the 2010s is we came out with this, we started using more and more this thing called deep learning. And specifically here, I'm talking about deep neural networks that we were now able to do more of because of even more compute and even more capacity to handle big data or data at scale or analytics at scale. And one of the reasons that I think we only start to see deep learning recently is, again, the compute and data is a big part. But another thing to think about is machine learning, typically when you get to a certain amount of data, its performance plateaus. So at a certain point, you can't take any more data and improve your model. But with deep learning, you can always improve the network and the model with more data. And you'll kind of see a little bit more of that as we get near the end. Now, a few spoilers, and this probably won't be spoilers to a lot of you who said you were already comfortable with the difference between AI, ML, and deep learning, but I just wanted to start off with these spoilers because sometimes I don't, and I think it might be more confusing than helpful. So this is the, in a nutshell, spoiler. You might have seen this in some form or fashion before. So like I kind of showed earlier, artificial intelligence is, the main topic here, which encompasses anything that's trying to mimic that human type of behavior like speech or language. And then machine learning is a specific part of artificial intelligence that is using statistics. And then we get even more specific with deep learning, where we're using neural networks, like I mentioned before. And then just a graphic, I kind of explained this a second ago, but with the amount of data, machine learning eventually plateaus, whereas deep learning can continue to improve. So this allows us to unlock, better insights as we get more data, or mostly as we get more data. Okay, so now we're going to talk about artificial intelligence. I'm just going to do a quick check and see if we have any questions. No questions yet, but feel free to ask questions at that site if you have them. Okay, so first we're going to talk about artificial intelligence, and this is a quote from someone in the 50s that was working at Dartmouth on AI. And again, like I mentioned, they said human intelligence can be so precisely described that a machine can be made to simulate it. And really the way that they were doing this was with symbolic systems. So think about logic systems, expert systems, simulation, and there was a lot of development that happened here, but a lot of it was just based on if-then type of really big statements or decision trees. And like I mentioned, as we kind of got more mature in time with machine learning and deep learning, we started to move towards more statistical approach. Now, when we talk about artificial intelligence, there are a bunch of different uses and what I'll call implementation families. So when you think about things artificial intelligence is capable of, you should think of decision, vision, language, speech. And I threw search in here, which isn't necessarily one. This list or this slide also conveniently happens to be all of the Azure cognitive services that are available. And for those of you listening that are not super familiar with Azure or Azure Cognitive Services, these are basically models that Microsoft Research has been working on for years, you know, in some cases, decades. And what we've done is we've packaged these models into APIs that you can call from your application. So this is what's called pre-trained AI. I like to call it either applying AI or using AI, because you're able to get the intelligence into your applications without having to go through this process of collecting data, creating a model, and making sure your model is accurate. You can kind of lean on Microsoft Research for that. The other thing I'll add in here is you'll notice that some of these cognitive services, so each of the little names are a different cognitive service, but each of these in black are kind of just used as they are. So there's no training or anything that you can do to make it better for your specific use case. But the ones in blue can be customized. So for example, if we take the language understanding cognitive service you see in the bottom right, this service, sometimes called LUIS, is used where they've created a base language understanding model. And so you just have to train it with details around your specific use case. So for example, we'll see a demo of an example for using this for deliveries. So maybe the base model has a pretty good understanding about places like cities and times, but it's not really sure of the context of like where a delivery is going to or where a delivery is coming from. So you could use LUIS to very easily create a model that can recognize to versus from in something like location, or that can recognize, take the word mon, for example, and find out that that's Monday, and not only that is that Monday, it's Monday, February 3rd. So these are just some of the ways you can customize some of the cognitive services. Now I do want to show a demo of language understanding as well as text analytics, which you can use for sentiment analysis. But before I do that, I think everyone is pretty familiar with SQL Server. Maybe not everyone is familiar with their extensibility architecture. So I just wanted to spend a minute talking about that. So a long time ago, SQL Server introduced something called CLR, which you can use to run .NET framework, basically to allow yourself to create T-SQL native type of functions. Now, let's see if I can get my mouse. So, nope, doesn't seem to be working. Here we go. There we go. Okay. So with CLR, CLR actually runs within the SQL Server OS. So there's a chance if there was some malicious activity or something blew up in your CLR, there was a concern that this would affect, in turn, your SQL Server and your data. So what happened is, starting in 2016, is we built this extensibility out. And so what that means is you would write T-SQL and say you want to execute one of these languages. And then what SQL Server would do is it would launch using a launch pad. So we kind of went with the rocket mentality here. But you could launch satellites, and these satellite programs, in 2016, we introduced R. Very soon after that, in 2017, we released Python, and in 2019, we released Java. And now, currently, we don't support .NET, but it's something that we're actively working on, and potentially even opening up this extensibility so you could write whatever language you want. Now, this could be for calling cognitive services and doing AI, or this could just be doing for whatever it is that you want to do programmatically. But I just wanted to give this primer because I'm going to show an example next of how I'm using a Java program in SQL Server 2019 to call a cognitive service. So with that, we will hop over to a demo. Yeah. Hopefully everyone can see that. Okay, I can't seem to see my mouse on my page. There we go. Okay, so another primer, for those of you that haven't seen Azure Data Studio before, this is Azure Data Studio. It's similar to SSMS history lesson, since SSMS came off of Visual Studio. Azure Data Studio has kind of come off of Visual Studio Code. So if you've worked with Visual Studio Code before, I know there were some developers, you'll notice this looks very familiar, and I can add a lot of the extensions that are available in Visual Studio Code, but I can also connect to different data sources like SQL servers or Azure SQL databases or PostgreSQL in Azure, among a few other options. But the nice thing about what I'm showing you here is called a notebook. And I think this is the SQL Server and data science user groups. So probably a lot of you have experiences with notebooks, but basically a notebook, they always end in IPyNB, and they allow you to mix Markdown. So you'll see this is just written in Markdown with code. So you'll see that in a second. One of the interesting things that Azure Data Studio has done is they've built out kernels for SQL and PowerShell. So you can create SQL notebooks or PowerShell notebooks. You can connect them to your databases or servers, and then actually save those results, as you'll kind of see if you haven't seen this before. But Azure Data Studio is super cool and super easy to use. They also came out with Jupyter Books, which can help you troubleshoot your SQL Server installations. Anyway, so back to what we were talking about, we're going to talk about adding AI to SQL applications with cognitive services. Now I'm going to go kind of quick on this. I am going to share all of my code with you. So I ask you not to get too bogged down into any code and just kind of focus on the ideas and the use cases around this idea of applying AI or using AI. So the first example I have is a sentiment analysis example. So I'm using wide world importers, and I have some reviews. Now, one thing I might want to do is determine which products I should invest in more or invest in less. And I might do that based on the review. Now, instead of looking at all these free-form reviews, it would be great if I could just call a model that could then tell me the review. So there is, within the text analytics cognitive service, the ability to do this. So basically what I did is I pulled the sample from the documentation for Java, threw it into my VM. This is just a compiled Java program, they end in jar, and created an external library that calls that. Again, don't worry too much, all the code I have. So now what I'm able to do is execute that Java program, which calls a cognitive service, and get the results in line with my data. Now I could add this as a column or create a new table or whatever, and then make decisions based on the values that are here. So that's one simple example. Now, a more complicated example might be with Lewis. So I talked about natural language understanding and how this allows you to actually create more custom type of models. So very quickly, what happened is I also have these delivery instructions. And you'll notice the delivery truck drivers, they put all their delivery instructions or notes in freeform. Now really probably goes back to my design of how they put these data entries in. Maybe I should have had a form to begin with, but if they didn't and we have all this data and instead of changing the system, we just want to get more information and insights, I could then create a Lewis model that could recognize, like if you look at statement 3, that could recognize that we're going from New York to Seattle and we're planning to arrive Thursday at noon. So it would be great if we could turn that into 2 like a from location and a destination, and a date and a time. So very easily you can do that with Lewis. I won't show you the Lewis model, but I included it in my GitHub, which I'll share. But same thing, I just created a Lewis model, called it from Java, and created an external library. And then we can call it on that same data and start to see some results. So we'll get our origin, destination, and the date time. So that's just one interesting way of, without knowing a ton of data science or about artificial intelligence or machine learning or any of it, you can really start to use AI in your applications. One note about cognitive service I didn't mention is these are available in containers. So if you're running in a Kubernetes environment or you need to scale the calls to your cognitive services, those options are available to you as well. I'll take a quick second if we have any questions.
You're on the air.
When you're saying Lewis model, you mean, is that language understanding model? Are you shortening something, or is Lewis an analytical technique?
Yeah, no, you're 100% right. Lewis stands for the Language Understanding Intelligence Service, which I think has since changed names, but the acronym has still stuck. I'm still talking about the cognitive service that does language understanding.
You used Java as an example, and I'm sure there are other languages. What is the thing that drives which language is available?
Great question. So you're right. In my example, I use Java. You can really use any language for calling cognitive services that can make API calls, because it's just API calls. And they have in their documentation, I think they have sample code that you can just take for a pretty big number of different languages. Now, if you're using SQL, that's going to depend what version of SQL Server you have. So if you're on SQL Server 2019, then you can choose between Python or R or Java. But if you're on an earlier version, you might be more limited. Off the top of my head, 2016, we added R. So anything before 2016, you won't have R, Python, or Java, but you could use CLR if that's something your organization is okay with.
Yeah, the question was that I thought you said you couldn't do CLR with this prior to your examples. You're saying that you can use CLR procedures inside your SQL Server to communicate to external services, or do you need an external service as a CLR app, a .NET app, to do your processing?
Sure, that's a good question, and what I was saying is the reason we came up with these external processes method of architecture is there were some concerns around CLR from some of our customers that they didn't want to run CLR since it runs on the SQL Server OS. Now, we have many customers today, even in Azure SQL Managed Instance, using CLR. So I don't think that's a concern for all of our customers. But yes, as long as you can make API calls, so in CLR, you can use cognitive services in SQL. Hopefully that answers your question.
It does. Thank you.
Awesome.
Looks like we ran out of questions for the moment.
Okay, cool. All right, so now we talked about using AI. We talked about cognitive services. We had some good questions, so I appreciate that. Now we're going to talk about machine learning. Now, traditionally, when you learn about machine learning, they might present some formal definition as follows. And I'm not going to read it. You can read it if you like. It's not very straightforward. So what I want to do is show an example, and I think a lot of you already have experience with machine learning, it seems like, from the limited poll, but we'll still go through this. Maybe some extra light bulbs will go off. So we're going to take an example, and we're going to try to train this machine. And this robot is my machine in this case. So what we have is we have some data. And what you'll see in the green is you'll see what we call features. This is a term data scientists made up to confuse other people. Really, they're just meaning columns or data that it can be used to predict whatever it is you're trying to predict. And whatever it is you're trying to predict, we call the label. So features are used to train your data and try to understand how that relates to the label. Sometimes you might call this in regression your independent variables would be your features, and your dependent variable might be your label. Okay, so we have some cups and basically some not cups, and we're basically going to try to train this bot to understand if something is a cup or not. So very simple example, we might feed all this data to our bot, and it might come up with a model that looks like this. So if the top is open, the bottom is closed, it holds liquid, and its hand size, it's probably a cup. So it'll tell us, it creates a model, and then we can show it something it hasn't seen before. So this is a slightly different looking cup. And it will use its model to basically determine if it thinks it's a cup or not, and then give us some sort of certainty. So here we see it does think it's a cup, and it's pretty certain that that's the case. So that's kind of the basics of how a machine or a bot would learn. And it's very similar to the way you might learn. You just might not think about it like this. So within machine learning, there's really kind of 5 questions or 5 areas that we talk about. The first is how much or how many. So you're trying to predict some sort of number, you're trying to do forecasting, that sort of thing. Regression, linear regression, logistic regression are probably 2 of the most popular forms of machine learning. So this is something you might be familiar with in the most simplest form when you try to create a line using y equals mx plus b. That's some form of regression. Another family is anomaly detection. So is it odd? This can be used in factories to determine if there's something wrong with the machine. This can be done for fraud detection. Lots of use cases here. The next is classification. So this is when you're trying to put things into categories and you know what categories they belong to. Here we're trying to put things into categories of birds, bikes, and tools. The last one I want to talk about that's part of supervised learning is which action should be taken. So more of a reinforcement learning or prescriptive type of analytics. Now these are all supervised learning models, which means when we train the model, we give it the label, which means when it's being trained, it knows the answer. So at the end of the day, it can hopefully get close to that answer. Now, the other type of machine learning is called unsupervised machine learning. And this is where there isn't really like an answer. And this is where you might try to figure out how should I group things together. So for example, when I go on Amazon and order the 8th thing that I've ordered this week, at the bottom, I might get a recommendation of people also bought similar things, or you might be interested in XYZ. And that's using that sort of clustering or recommender of trying to group people and things together. So unsupervised learning is that one, and then the other ones are supervised learning. So there's actually some sort of answer we're working towards. Okay, so now just to do a demo of machine learning example. Again, I'm going to use SQL, but this time I'm using Python. Python is something you guys are probably familiar with. The debate between Python and R continues. But this example is predicting wine quality. And this is based on a public data set. So if you want, you can go and try to play with this data set as well. there are lots of data sets that are free and that people have competitions on the internet. If you are looking to just play and get started with machine learning, that's definitely a great way to learn. Okay, so just brief setup. I did this running SQL Server on a Linux virtual machine, and I was using the Python package. So I won't go through all this code, but just know that I have it all. The big thing to point out here is this get compute context and set compute context. This means that even though I'm using Python on whatever installation of Python I have, I'm able to set the compute context of SQL Server. So that means I don't have to use my local compute context. I can use the compute inside my SQL Server instance, and I can also prevent myself from having to move the data out so I can process it in Python. And I can actually do in-database machine learning. So that's a big reason people move towards SQL Server machine learning services, because you can do in-database machine learning. Now, again, I'm not going to get into all this code, but basically, once you get the data, you're going to want to look at it. You're going to want to look at the different properties. So here we have different chemical properties and physical properties. And then in our case, the label is quality. So we're going to try to predict wine quality based on some chemical, some of the details about the wine, so that maybe we can decide which wines we want to stock in our wine shop. Just some example. So I looked at some red wines and some white wines, and again, we're skipping around here. And then I created a histogram to see if there was, any interesting things here. Mostly what I found is there are a lot of mediocre wines and not a lot of really good or really bad wines. This is a joke that usually goes over really well in person, but because this is remote, I have no idea if anyone laughed, but I'm just going to assume that you did, and we'll keep going. Okay, so once you've looked at your data and you're ready to start making a model, one of the nice things about the packages here is I can actually use those scikit-learn packages. So those of you that worked with Python are familiar with this. I can use this and apply it in database. All I have to do is basically wrap whatever I want to do in a function and then call it on the data I want to run it in and the compute context of SQL. Again, won't get too deep into this, but just know you can use whatever Python libraries you like when you're doing in database ML with Python and SQL. You just have to wrap them in functions. Okay, so now we create a regression model, and I'll skip most of this, but now we can make a prediction on unseen data. So this is on our test data. So this quality score here is the actual score, and this is our predictions. So not too bad for just a quick create a model. We can also then do things like look at the R-squared value, and there's a lot more stuff you could do here. This isn't, all of machine learning, but it's a big part of it. And we'll skip some of this. You'll also try to find a different model. I talked about using the testing data set to pick the best performing model on unseen data. But we'll skip that for now. Just an example of how you might use this. And then I just wanted to mention this package we have called SQL ML Utils. If this is something that you're doing, this allows you to take Python code and easily deploy it as a stored procedure in SQL Server. Otherwise, you have to write it in yourself. But basically, when I run, again, I wrap my Python code in a function, and I run this create stored procedure from function. It then shows up in my SQL Server with all the formatting and T-SQL that's needed to do that. So again, just a quick example. Hopefully get some ideas flowing of some of the things you might do with machine learning in SQL or machine learning in general on data that you have. So again, I'll take a brief pause and see if there are any questions.
Looks like we have a first question.
Just a simple one. Have you tried doing any of this stuff on Docker?
Doing any of this on Docker.
Any of the
So
experiments of working with it, setting up the Python scripts and having an environment with everything involved in containers?
yeah, sure. I mean, the question is, do you use Docker and Python together? Is that what you're asking, or Docker and SQL and Python together?
Python, SQL, deep learning with the tooling that you have on Docker.
Yeah, I think Docker is a great tool for this. I don't know if many of you have used SQL Server 2019's big data cluster capability, but basically what they did is they deployed SQL and Kubernetes, and they have a data pool and a compute pool and all that stuff. But what I've done is I've actually deployed containers into that Kubernetes cluster. So then you can kind of scale the deployment of your models. Personally, I haven't used containers as much for training models, but I could definitely see a use case for that. Certainly deploying to containers and then to your applications, whether or not they're SQL, is something that's very common.
I think it's more for preparing data in terms of doing crunching, throwing them out, and then when you're done with those machines, tossing them. Basically setting up the data, cleaning data for your processing.
Yeah, so I think the comment is, could you use it for setting up the data, processing, and cleaning? And I think absolutely, yeah.
Cool, thank you.
Yep. Next question over here.
Typically, like, we take data from SQL Server, put it in some kind of like CSV kind of thing, and then actually process it in Python. But interestingly, you're here and mentioning that we could rather do the other processing in SQL Server. So I haven't not done it, but like, what would be the reasons to do that? And would you see better, would you be able to use GPUs and things like that with that? If you do that?
So I think the question is, currently we take SQL Server data out of SQL Server and run it in Python outside of SQL Server using whatever compute that we need. Is there a reason for doing it in SQL Server? And I think the reason for doing it in SQL Server is when you start moving data, especially when you have a lot of data, you start getting into all sorts of different problems around actually moving the data, the fidelity of that data, the more times it moves, potentially more issues you might have. So I think ideally you would set up your infrastructure to be able to train and deploy without having to move that data out of SQL Server. I know that's not always possible because to a certain extent it will depend on the infrastructure that your SQL Server is running on. But that being said, if it happens to be running in some sort of Azure system, then you can more easily tap things like GPUs or FPGAs. But I'm not exactly sure how easy that is to set up connections to GPUs from within SQL Server. I know in big data clusters, it's something that we're working on. But in SQL Server today, I'm not quite sure. I'll share my info at the end, and feel free to reach out to me because it seems like you have a good use case for potentially doing that.
Thank you.
Got a couple of questions in chat. The first one is, so you showed an example of creating a stored procedure using Python. Could you do the same thing in R?
Yeah. So you can do the same thing in R. If you actually, what I can do is it's an open source package on GitHub. So let's see how this works. So if you just do a quick search for SQL ML Utils GitHub, you'll be brought to it. And it has support for R and Python. So yes.
Okay. The other question Is scalability the biggest advantage when taking this to containers, or is there another reason why you might want to use containers as well?
Personally, I think there's a lot of advantages to running in containers. Scale is a big one from a DevOps perspective, for a dev testing perspective. Containers can be very valuable. If you look at the way technology's going, my understanding is the future is going more and more towards a Kubernetes type of world. So yeah, if you're not familiar with containers, it's definitely a good thing to get familiar with and start playing around with.
Okay, thank you. I think that's all the questions. Everybody's avoiding eye contact like they don't have questions.
I see 2 questions in my Q&A here. One is, how accurate is the sentiment analysis scores? Are they good for different industries? And I think that's a great question. I think at the end of the day, you need to test the cognitive services APIs in your use case and make sure they are giving you a good result. If they aren't, then you can look at something more custom, like creating your own machine learning or deep learning model for that. Then the next question I see is, what's the best way for a SQL developer to get familiar and hands-on with AI and ML in SQL Server? That's a great question too. There are a few tutorials in the documentation. There's also something that myself, Bob Ward, and Buck Woody have been working on for over a year now, called SQL Workshops, and I'll share that and some recommendations of how I think you can get started there. But basically, there's a ton of resources online to learn whatever it is that you want to learn. But hopefully, I'll give you a good starting point. And if there's no other questions, we will continue. Okay, so we've talked about AI, we've talked about ML, now we're going to talk about deep learning. And this is the one where I'm going to show the most math, but I want you all to remember that no one is expecting you to either memorize this math. The point of showing the math is just so hopefully something clicks in your brain and you're like, oh, I understand at a very high level how deep learning works. And then you can start, using or playing around with it depending on how deep you want to go. Okay, so we saw how potentially machine learning or artificial intelligence can be really good for a lot of use cases, like, for example, recognizing dogs. Now, as these dogs get more complicated or more difficult to identify, in this example, it can get more complex, and machine learning models might not be able to identify them as easily. For example, I had the honor and joy to go present at SQL Saturday South Africa in Johannesburg, and we did like a small safari, and there was one point where we were trying to find wild dogs, and I don't think most machine learning models would be able to pick up the wild dog in here. Actually, when I first saw this picture, I could not find the wild dogs. Sure enough, the wild dogs were in there. I think it's actually, now I see it, it looks like there's actually a pretty obvious one right there. I just never noticed that. But the point being, like, when things get more complex, it gets harder in some use cases for machine learning to kind of hit the mark that you need to hit. Now, I was trying to think of some common use cases, and I did a little research on what are some of the common use cases for deep learning. I know there's a lot of things up on the page. What you'll hear a lot about is image recognition, or voice recognition, or speech processing. But there are a lot of things as well in different industries, like medical image analysis. This can be used for analyzing things like x-rays and other types of scans. Localization and mapping is a big one. Even sometimes automating things like social media. So maybe some of you saw the not so successful Microsoft attempted this a few years ago. I think it was Tay. Can't remember, but sometimes it works, sometimes it goes pretty poorly. As well as things like converting paperwork into digital data. This is a big one these days, or things like autonomous vehicles. Deep learning is a good or commonly used for these types of things. So again, hopefully this just starts getting you thinking about deep learning uses. Now, the first thing you have to do when we think about images or vehicular object detection or image analysis or anything that involves any sort of image, we have to first turn that image into a number. And many of you have probably worked with files at some point in your careers and are familiar that oftentimes file images are broken up into pixels, and then those pixels go between 0 and 255, I believe, which represents a color. Now, for whatever reason in the data science world, having a 28 by 28 image, which is a total of 784 pixels, is very common. So you'll see that a lot if you go and start to play with this on your own. But what we do is we basically turn every image into a big matrix of numbers, and all of these numbers become our features in a way, if you remember. So these all become input variables into our neural network model. So basically, you'll take this big image and turn it into one string of a bunch of numbers. And then, let me get my laser pointer. And then each of those pixels, so this pixel 1 is 0, each of those pixels will be fed into the neural network. So this is just simulating a first layer of a neural network. But the main takeaway here is that first we have to change everything into a number. And if the image is a colored image, then there are multiple layers of this image in the image. So it's a much bigger number. But for now, we'll just look at black and white. So now we're going to kind of break down the process that happens in deep learning. And I'm going to start by actually using a really not deep neural network, just because I think hopefully if you understand this one, the rest will make sense. So what first happens if we have those inputs? So those are, for example, the pixels from the previous image. We just have 3 inputs in this case. And then you'll have any number of hidden layers. In this case, this model is actually just considered a 2-layer model. This layer doesn't count. So we have our hidden layers. There could be much more than one. There could be just one in this case. And then we have our output layer, and then we have an output. So in the previous example, if we were trying to identify which digit that would be, we would have 10 outputs, 0 to 9. And the output would basically be a confidence score of which one the neural network thinks. So hopefully the kind of output corresponding to the number 8 would have a very high probability, where everything else would be close to 0. So that's kind of what our network looks like. We have an input layer, a hidden layer, and an output layer. Okay, so what exactly happens in this input layer? Here's our first step of math. So again, if we look over here, these x1 to xn would represent our same inputs or our pixels in the other one. And now each of these lines has an associated weight with it. And at the beginning, these weights are just random numbers. Okay, so we have a random number, and then the way we combine them all together is using this, it's a dot product, which I'll show you in a second. But basically what we're doing, if you just look at one input and one weight, what we've done is we have the input times the weight, and there's also this thing called a bias. So that's a plus B. You'll never see them put that in here because there are B's everywhere. Really what we have is we have the equation for a line, if you remember, mx plus b. And even though our m or our slope or our weight isn't correct at the beginning, that's kind of what we're working towards. So at the lowest layer, we've got a linear relationship. Now that when we combine all of those inputs and all of those weights, it looks like this. This is really a dot product, which if probably a lot of you don't remember dot products from a long time ago, but basically you multiply each of the corresponding input and weights together and then sum those all together. And this also takes into account your plus B, plus B, plus B, plus B. Again, they just don't write that. So at the end, we have sum, and this is just one neuron, okay? So this could be, for example, just this one. So this one's going to take in the input and the weight and the bias and go here, the input and the weight and the bias go here, the input, the weight, and the bias go here, and sum that all together. So that's what we get here. Then what we do is we use an activation function. So this could be a very big number or a very small number. It could be a very positive number or a very negative number. But at the end of the day, we just want to know, was this thing fired or not? So kind of think of it like a neuron, like is it firing a signal or not? So we use something called an activation function. And here comes some math, but one of the common ones is called a sigmoid. Don't worry about this too much, but what I want you to notice here is if you have a number that's, you know, pretty big or not even that big, your result is going to be very close to 1. And if you have a number that's small, your result is going to be very close to 0. So this activation function is basically scaling our output for that neuron to between 0 and 1, and probably pretty close to 0 or very close to 1. So then we get an output y. So where are we at this point? So we were looking at this one. We did our sum, and then we did a dot product. Let's say it came very close to 1. It's like 0.98. So now 0.98 becomes the next input into the next layer. So now we'll have all new random weights, and we'll have an input here, and we'll multiply by the weight, and input here by the weight, and so on and so forth. And we'll basically do that for every single neuron in the network. And at the end, whatever that output is the output that we'll put out. So what we call this process is feed forward, because we're making our way through the network, you know, forward through the network. So we've done this once now, but the problem is all our weights were random. So probably our output was not very good. So the next thing we do is called back propagation. And there are a few things that happen here. First, we want to figure out how wrong were we, right? So we use something called sum of squares law. So this is the actual value. This is the predicted value. We take the difference and we square it and we sum it for all our outputs. So that's how we get this. So that's called the sum of squares loss. Now this is interesting, but it doesn't really tell us how we should update those weights. That's where the derivative comes into place. Now, usually I get to quiz people on what a derivative is. I won't do that today, but think about it if you know, maybe tell your neighbor if you know what a derivative is. Maybe there are some key indicators up here, but basically a derivative shows how something is changing. So what we want to know is how loss is changing with respect to how we change those weights. So basically what that amounts to, without getting too much into it, is taking the derivative of this with respect to x, so with respect to our inputs and our weights. So this turns into a pretty complex derivation. You might be able to see the beginning of it is 2, this 2 comes down, and that's how you get this part. But the rest gets a little complicated, and I'm not going to show it on the screen. If you also remember the chain rule, which I might be giving you some PTSD from calculus, the chain rule is how you can calculate this. It's an interesting derivation, but it's just kind of not interesting to this. But basically what we're trying to figure out is the derivative of loss with respect to our different variables and how it's changing. And what this allows us to do is figure out how we need to update our weights so that we decrease our loss. So we make our loss as low as we can, which means we get as least wrong as possible. And that's something you may have heard of called gradient descent. So that's kind of what we're doing here. Again, lots to read about gradient descent. I just want you to understand that we use how loss is changing to determine how we update our weights. So based on that, we calculate new weights based on our old weights plus the derivative of loss. So how those weights are changing so that we can minimize, how loss is changing so we can minimize the loss or the overall being wrong. And the way we do this is we go this way. So we go right to left through the model. So at every point, we'll determine the loss from, so here we'll determine the loss from the actual, and then we'll figure out how it's changing and propagate that back with new weights here by updating these weights. Then from there, we'll do the same thing here. We'll calculate the loss as compared to what it should have been coming out of here. And then we'll calculate how it's changing in order to update the weights. And you'd go through each of the layers like this, and that's called back propagation. So at the end of the day, you do feed forward. So you go through the model and see how your weights perform. Then you use how they perform to update your weights and do back prop. And you do this over and over and over again. Sometimes, you know, thousands of times. You might have many layers in here, and many inputs and many different nodes, and there are different ways you can configure those hidden layers. But just so you see, hopefully you're seeing why the amount of data is so high and also why the amount of compute that is needed is so high. I'll take a brief pause and then I'll show you how it works in Python. And I'm not going to show like TensorFlow or PyTorch or Keras or anything like that. I'm just going to show you good old-fashioned Python. We will write this part in Scratch.
There is a question here, since you're transitioning over to a demo. Are there different types of activation functions?
Yeah, that's a great question, and probably something I should have mentioned. There are several different activation functions. The one I talked about was sigmoid. Another one that's very common is ReLU. There are other ones as well. I don't know if there's really a science over which ones are better for which use cases. I think people experiment with different things. But yes, there are multiple, more than one and more than two.
Yeah, I just remember ReLU being nice because it has a faster transition from one state to the next, if I remember right. So, like, there's some oddities with sigmoid and TANF around where your slope hits a certain point. Been a little while since I had the last fake that answer.
No, I think that's great. You're 100% right, and I think there are people who have opinions and there are people who have proven things, and I would still say jury's still out on if one is like the main go-to. But I would say ReLU is probably used the most frequently.
Great, thank you.
Okay.
There's another question as well.
Yeah, sure.
How do you define the number of the hidden layers?
Yeah, so the question is, how do you define the number of hidden layers? I would say that's probably a little beyond the scope of this. A lot of it, and you'll hear people say this, like a lot of this is not necessarily a science yet, but more of an art. something interesting to do, and if we have time, I'll show one example, is to go look at the competitions of, they have competitions on different data sets around creating the best neural network, and to see the combinations, you know, and I know it sounds terrible to say this, but a lot of people say, just like data analytics, like to a certain degree, some of this stuff here is an art, and it's more of a, you know, trial and error than it is really a science. And I don't know that there's really an exact science to how many layers. There are different combinations of things that you can do in the layers. For example, there's one method where in certain runs of feed forward and backprop, you turn neurons off. So there's a lot of techniques that we won't really get into today, but it's definitely like a great question and a great topic.
All right. Any other questions? Nope, no other questions at the moment.
Cool. Let's see some Python. Okay. So this last example I have, again, is we're going to build a neural network from scratch. The only library I really use is NumPy. This is a very common library, similar to Pandas if you worked, similar in popularity as Pandas if you've worked with Python. But what we're going to do is basically first define two functions, sigmoid. This should look familiar because it's just the sigmoid function. And then the derivative of sigmoid, we didn't actually derive this, but it actually works out to be a very nice function. So we're just defining those so we can use them later without writing all this out. And I will give this notebook to you all so you can run it and play with it too. There's lots more resources in it. But what we're going to do is create a neural network class. And so we're just going to kind of define the initial state of this. So what we do is we take in the inputs, which is X, and we label it as the input. Then we create weights. So remember, this is two layers. So we have two sets of weights, and we're going to make those weights just based on the shape of the input. And then we're going to do that for weight 2 as well. So we'll have two random sets of weight. We'll set our y is y, and then we'll just kind of zero out an output, which we'll fill in later. So just simple Python initiating this class. Okay, next what we're going to do is add the feed forward part. So if you remember in feed forward, what we do is we take the input and we multiply it by the weights in that layer, and then we sum them all together. So here I'm using np dot, so it basically does the dot product between these two, which is the same as multiplying them, then summing them all together. And then I'm applying that activation function on top, which is that sigmoid. So that's how I get the layer 1 output. Then I take that layer 1 output and I apply it to the next layer. So I have my layer 1, I multiply it by the weights in layer 2. And then I take the dot product, so sum all that together. So same thing in step 1, but we're using a different input. Then we take the activation function on top of that, and we get our output. Note, just for simplicity's sake, I did leave out bias here. I just assumed bias is 0. Just adds another complexity in this demonstration. But typically you would add bias here as well. Okay, so this is where if you want to learn more about gradient descent or chain rule, or how we did that derivation, or how we decided we were going to minimize our loss, I have some references here and some explanations. You can check for that. But for now, we're just going to add it. So remember, what we're doing is this is the start of that derivative of loss, if you recall. And we're seeing how it compares with the output to layer 1. And we're doing the dot product. And that gives us the how loss is changing based on weights 2. So basically, how should we change weights 2 to make the loss smaller? And then we do the same for weights 1. It's just a little more complicated because we're also applying it to the stuff up here. I'll let you guys review that later, but we won't get into it here. But then, like you saw on the slides, we're taking weights 1 and updating it. So this basically means take this and keep this, but add this to it. So basically take your weights 1 and add the du weights 1. So this is the derivative of weight of loss changing as with respect to the first layer of weights, and that's how we update those weights. And this is called the back propagation, which we saw. And then I talked a little bit about this digit recognition thing. I wanted to pick a more simple example. So what I did is, instead of having a 29 or 28 by 28 image with a bunch of pixels and a bunch of things, I just said, let's figure out, based on different images, if it's an L or not, if the image has an L, contains an L somewhere in it. So you guys can probably all obviously tell image 0, image 1, and image 4 have an L in it. Image 2 and 3 have backwards L's in it. So we're going to say those are not L's. Okay, so like I said, the first thing you have to do is turn these images into numbers. So how I did that is I put them into a grid and then basically assigned 0 to white space and 1 to blue space. So if image 0 is to turn into a number, it's 0, 1, 0, 0, 1, 1, 0, 0, 0. And I did that for all of the numbers, and now I'm able to create a matrix that contains all of my data. So this is that matrix actually wrote out visually, but you could see the numbers that I'm assigning to it here. And then I can create one array. So that's what we've done here, is basically taken those input numbers. So those 9 numbers are here for that first value, and then given it a label. So the label for this one, if you remember, image 0 was a L, image 1 was an L, and image 4 was an L. Now, some of you may be able to identify a pattern here, but others might not be able to do it visually, and that's fine. So what we want to do is try to train a machine to recognize the pattern that is here. Anyone in the audience see the pattern and want to share what makes an L and what makes it not an L?
I'm gonna make a fool of myself and say that you have a single blue spot followed by 2 white spots followed by 2 blue spots, which makes for an
There
L.
you go.
Oh.
Yep.
Yeah, that's all.
Do other people see it now?
The recognition's happening.
Yeah. So an L has a 1 blue, like Kevin said, followed by 2 white, followed by 2 blue. And things that aren't L's just don't have that. So these 2 were not L's, so they don't have that. But the other ones were L's. So image 0 has it, image 1 has it, and image 4 has it. Cool. Not that you need to do that. That's why we're training machines how to do it, but just kind of a fun mental game. Okay, so now we have our data set, and I've printed out the data set. So basically we have our features. Those are everything except the last column, and then our labels. Again, that means image 0, image 1, and image 4 are L's, and image 2 and 3 are not. So now I'm basically going to initialize this neural network given the X and Y data. So again, the X data was our features, the Y data is our labels. And finally, what we'll do is here I'm cycling through 400 times of doing feed forward, then back prop, then feed forward, then back prop. And those are those stages within that neural network class we created. And then what I'm outputting is for I in range 0 to 5. So this basically says for each image, display the confidence that the neural network is that that image is an L. So very quickly, we can see that the neural network is more than 96% confident for image 0, 1, and 4 that it's an L. and it's very unconfident that 2 and 3 is an L, which you could flip this and say it's very confident that it is not an L. So again, just a super quick example to see how this actually works. And there's lots of references in this notebook if you want to go read deeper, but the point here is that now you've kind of seen, hopefully, how it works, and you can start applying different things. I'll pause. Any questions? I will.
Looks like no questions here.
Okay, everyone's glazed over, and if you're at home, you've decided to do something else. Just kidding. Okay, so we took a look at a very simple example. We just had 2 layers. Now let's look at an example where you have lots of layers. For this example, we are trying to do facial recognition. So the input layer is a 28 by 28 pixel image of a person's face, and then we run it through our neural network. We do a bunch of feed forward back prop over and over again. Like I said, we might enable or leverage other techniques like turning certain neurons on and off in certain feed forward and back prop loops. We might add different activation functions at different layers. Lots of different stuff we can do here. But after many iterations, and as your neural network starts to get very deep, your hidden layers might start to represent features. And I know you're probably all very familiar with features now, but just a quick reminder, features for the cup were like, does it have an open top? Does it have a closed bottom? Does it hold liquid? Is it hand size? That sort of thing. So that's what we talk about when we say features. So what you'll see is some of these layers might start to look like things like edges, and then as you go deeper into the layers, probably not the second layer, but maybe much deeper into the layers, you might find combination of edges, and maybe these combination of edges are starting to represent, I know it's small, but like a mouth or an eye or eyebrow or noses. And then when you get super deep, you actually get kind of these layers that look like object models of different people's faces. So that's one of the really interesting things about these layers, and a lot of times you're not really sure how these layers will turn around, come about. I think we have some extra time to do this, so I wanted to show something I found that was really interesting. What it was is, where is it? They visualized layers in a very deep, complicated model. Okay, and I'll share the link to this. So this is layer 7. So if we look at layer 7, we're not seeing much here, except maybe we're seeing patterns. Now, as we get deeper, so now we're layer 14, we're seeing more patterns with more colors. So this would be for a model that for images that do have color. But what's interesting as we go through this, and I'll kind of skip ahead a little, is, I mean, apart from seeing really wild visualizations, so what we're looking at is a hidden layer here. So how all of those map to an image based on each of the neurons. But you might start to recognize things that look familiar, like maybe this looks kind of like a leaf, or you know, hair, or different things. And as you get even deeper in the layer, so now we're down at the end, you can see things like eyes maybe, or other things in here, maybe chains here. But you can start to get a lot out of these neural networks. And I still think people are researching how to interpret these and then how to go back and implement them into a better model. But some interesting patterns that this guy noticed is, for example, this looks very similar to him to arches. So maybe this was a layer that was helped to use to identify if there were arches in the image. And for that image, you can see it was really activated. So the mean activation, so this means after the sigmoid or the ReLU, the activation for that layer was, that filter was super high. Lots of other interesting things in here, like this one kind of looks like Rooster, and again, you can see how those filters are pulled out. But anyways, there's a lot of cool stuff in here, a lot of cool things you can gain from the layers. I will share that article. It's just a really interesting read. I think that's one of the exciting things about this space as well, is that it's still pretty new and there are so many people writing about it on sites like Medium and other, you know, open blogging sites. So there's a lot of places to learn and explore, and the community isn't quite like a SQL community, but you know, it's pretty good. Okay, so we've talked about AI, ML, deep learning. You've seen some demos. Hopefully I didn't melt your brain with math. But now I just want to spend, you know, kind of a few minutes talking about the platforms and tools from a Microsoft, from an Azure perspective that might be helpful here.
We do have one question that's around
Yeah.
hidden layers. So why is it actually called a hidden layer and not just a layer? Like, what's the hidden part mean?
Yeah, I mean, I guess that's a good question. I guess when you see the layer, the filter, then you're like, well, I thought it was hidden. But I think really, I don't know the answer to that question. I would just be making something up. But at the end of the day, like, you see what you put into the model and you see what you get out of the model. And necessarily you wouldn't be able to apply a layer as an answer anywhere. For example, you might have hidden layers that have like one layer might have 40 neurons, one layer might have 100 neurons, and then your output might only be, you know, the 10 digits that exist. So sometimes it's hard to map a hidden layer to an output. That's my best guess, but that is not, like, I would have to, I'm sure there's a Googleable answer there why they're.
All right, thank you.
Yeah. So if we talk about some tools, the first one I wanted to mention is the data science virtual machine. If your organizations or yourself as a company have access to a Visual Studio subscription, a lot of times those come with free Azure dollars. And if you aren't using them for anything, this can be a good investment because they only charge you when the virtual machine is on. So if you're familiar with Azure VMs, it basically gets billed like a standard VM, but it's packed with tutorials, with AI tools. And this is something where you can actually leverage things like GPUs and FPGAs. They have ones that are built for Geo. So this is a really cool way to learn and also to implement data science. For me, this is like my go-to VM if I'm creating a VM, just because it's already loaded with everything I need. So you can learn more about it at aka.ms/dsvm, but there's been a lot of Microsoft investment to put a lot of stuff in here. So if you're learning or want to use it, I think it would be good investment. The other thing I wanted to talk about is just some of the services that we did and didn't talk about. So we did talk about some of the pre-trained models or being able to apply AI with cognitive services. Again, as long as you can make an API call, you can use a cognitive service in that sort of application or workflow. They also have these built in a lot to Azure Functions, which makes it super easy to use them if you use Azure Functions. There's also popular frameworks. We support them. We work a lot with Onyx, and then we support running things on TensorFlow and Keras. Now, if you're not familiar with these are basically really popular frameworks that are used for doing deep learning. And they have packages and libraries that make it really easy. So you don't actually, in the real world, have to write neural networks from scratch like you saw today. You can use a lot of the pre-existing libraries. Then we have some services. I talked a little bit about the data science or machine learning VMs. There are some other services you're probably familiar with. And then we have infrastructure, and the nice thing is you can just pay for it when you use it. You don't have to make investments into FPGAs and then pay for it while it sits unused 99% of the time. Um, that's most of my spiel. But again, I'm coming from the SQL team and I'm a SQL person and I'm talking to a lot of SQL people. So I'll just stress that there's a lot of capabilities within SQL today that can allow you to take advantage of a lot of the statistical and machine learning sides. And we're working on things to support more of the deep learning side, which I think you should be seeing in the next year or so. And finally, one of the really nice things is that you can kind of train and deploy it wherever. It's one of the few products, SQL, that's actually available at the edge. So we have SQL Database Edge, we have SQL in the cloud, we recently have SQL in a more hybrid sense with Azure Arc. So, you know, you guys have been working with SQL probably for a long time. So that's one of the benefits of doing things with SQL. So I'll get off my SQL stool now. We will have a brief pop quiz now. I know it's hard to do these pop quizzes in a remote environment. So if anyone cares to come off mute, we're just looking for a summary of the different terms that we talked about. So data science is.
I'm unmuting. We have a taker.
Okay.
Data science is a combination of statistics and computer science, and it can use data analysis with some scientific methods to derive some conclusions.
Awesome. I love it. Great. You guys can stay unmuted if you want to keep contributing. Okay, we also talked about the team data science process.
Team data science process, anyone?
It's the Microsoft framework used for deriving their knowledge nets and what have you. It's an entire process for machine learning, for their modeling and everything else that they do with data science.
Yep, that's about it. It's Microsoft's recommended data science lifecycle, and we do have like code samples and project guides and tutorials and all that stuff too. Artificial intelligence.
So there's a question about team data science process, I think.
Sure.
Would there be other examples? You had excellent examples today. Like, would there be other examples for Q&A Maker, text analytics, custom vision, and the personalizer, some of the other products?
Are you asking if there will be better data science lifecycle related samples for Q&A, custom vision, etc.?
Yeah, or tutorials or documentation online or Jupyter notebooks like you showed today.
Yeah, I mean, I think that's a good question. I think the teams work hard on getting those samples out, but if there's anything that you want to see more of or you think is missing, I'll share my info and we can definitely, you know, work to make that happen.
Okay, thank you.
Okay, artificial intelligence.
Anybody want to take this one?
This was one of the bigger umbrella terms that basically just envelops mimicking anything that would mimic human behavior. So mimicking speech, vision, reasoning, that sort of thing. Machine learning, I can pick it up if people are tired of participating, that's fine.
Machine learning is using of different features or variables to predict the future or to predict an outcome. It's just as simple as that, you know, using a regression or something.
Yep, being able to make predictions from data using statistical methods and leveraging the features and sometimes labels. Yep, nice. Neural network.
Okay.
Yeah, go for it.
Neural network is something like complicated machine learning. Instead of having input, having output, you have input with some hidden layers in the middle, and then you get the output, and then you have a cycle of repeated forward and backwards to get the best prediction possible.
Yeah, I think that's great. I had a really low bar for a definition there, but I think yours is better. Okay, a deep neural network, we'll skip this one because you kind of got to it. Neural network with a lot of hidden layers or multiple or some combination. And then my final point is that Azure and SQL Server can help. With that, I do have one more poll. This is just for me, really. It's just an open-ended question that's anonymous where you can tell me how you think I can improve. I'm new to these remote type of presentations, so I'm always looking to get better. The other thing I will share is the two resources I kind of talked about. I will show you in a browser, and then I will put the screen back up. Okay, so the first is SQL Workshops. So if you go to that first URL, what you'll see, and this is what I kind of mentioned earlier, this is something Bob Ward, Buck Woody, and myself have been working on. We have some workshops that are available, so SQL Server Ground to Cloud, if you want to run OpenShift 2019, and these have hands-on labs, they have presentation materials, they have slides. Like, we're happy if you would use these to learn or teach, or you could even spin up your own training company and get paid. Like, we would just be so happy. Bob and I are also working on an Azure SQL workshop, and we have some labs. What might be interesting for this crowd based on this presentation is we have a few workshops and labs for our Python as well as SQL Server 2019 big data clusters. This gets a lot into machine learning in a big data sense. And then for some SQL developers or people just getting started with SQL and machine learning, I think this is a good reference. So that's one reference you have. The other reference is that I will give is aka.ms/analytics. That's a link to my GitHub. And in my GitHub, you can find all the presentations I've done in previously, as well as all the code for them. So in TriPASS is where you can find those notebooks I went through today, as well as the slides. In SQL ML, you can see full info on how to set up that Java program, how to do ML with R and Python. Oh, this one's not Java, in R and Python. There's also ones for Java using cognitive services and containers. So there's a lot of stuff in here. You can kind of read what's in it here. So those are the two main resources I recommend checking out. The other thing I'll say is, like, feel free to use me as a reference. I'm happy to help in any way that I can, whether it's getting the right things or information you need from Microsoft, or if it's just general insights or whatever. I'm around. Add me on LinkedIn. And thank you so much for taking time out of your Tuesday night in Raleigh. Oh, I think there's one fun fact I left out, is that I'm actually from Raleigh. So it's really cool. Maybe one time I'll get to come in person. But yeah, with that, I will wrap off and pass off to Kevin. And if there are more questions, I'll stick around. Thank you.
For comments.
So the question, actually, if you could repeat the question.
You said you were going to do something on Slido for getting some feedback for yourself.
Yes, if you go to slido.com, and then you have to use a different code because I wanted it to be completely private and anonymous. Yep, thank you.
All right. Thank you very much for your time, Anna.
Yep, thank you. All have a nice one.
Thank you. Thank you.
No, I was making a joke about it.
All right, so wrapping up tonight, because I did mess up the introduction, I was on mute the whole time. That happens from time to time. SQL Saturday Raleigh is going to happen April 18th, Wake Tech RTP. So check that out at SQLSaturday.com. Registration is free. Lunch is $15. That is optional. We're going to have a slate of excellent speakers on a whole bunch of different topics. So SQLSaturday.com, look for Raleigh 2020, and register today. And with that, we're going to end tonight's stream. So thanks everybody for tuning in, and we'll catch you next time.